Welcome to Monday Night Calculus. My name is Curtis Brown, and I have with me, as always, the Steve Kokoska and Tom Dick. Super excited to have those guys here. We've got some great calculator tips for you for the AP Calculus exams and for the content exhibited on those exams. We're going to be looking at differential equations tonight. So, fun title tonight, Hit the Slopes. I imagine that may point us towards a few slope fields, I think among other things. So excited to see the content that we're going to be looking at tonight. Steve, I think you've got the problem set. So
Okay.
away.
Thank you very much, Curtis. Great to be with you and Tom again. Happy St. Patrick's Day. I'm not sure.
Same to you.
I'm
I
not.
wore my green. I don't know about
I
you.
got some green.
Okay.
But listen, Curtis, if you didn't do your homework, we might have to ask you to sing an Irish song. I don't know. So be
I don't
prepared.
know very many Irish songs.
Okay. Well, we do have some good problems tonight. There's a lot of good, I think, technology here, and Tom, I think, has agreed to show us some stuff with both the TI-84 and the TI-Nspire. So I'm going to try to get through problem one, doing a few things analytically, giving you a couple of things to think about, and then I'll turn it over to Tom. So let's start out by taking a look at this differential equation. dy dx is y minus 1 times the sine of x, and the first part of this is to sketch the slope field for this differential equation. Hey, notice that the slope field's in green for St. Patrick's Day. How about that? So you certainly want to do something like this using technology. And again, Tom will show you a little bit about this with the 84 and even with the TI-Nspire. But there are a couple of things that I'd like you to think about. I produced this slope field using Mathematica. And as Tom has some go-to windows, mine for producing slope fields is often -3 to 3 in both directions. And so I used that here, and I could have made it denser, but I think this gave me enough idea about what a solution curve might look like. But there are some interesting things to look at here, to think about. The first one is right here. As I look along this line, y equal 1, it appears to me that all of those line segments have slope 0. And so you might think about, does that make sense? Can I justify that? Do I see why that's true? And another thing you might think about and see here is if I look along, hey, the y-axis, where x is equal to 0, it also appears that all of the line segments have slope 0. So can you justify that? Does that make sense? And there's one other thing that I'd like you to think about. I'm going to come up here to the equation, the differential equation. I'm going to circle this sine x. There's a product there that involves the sine of x. And so when I thought about this and I produced this slope field, I was looking for some sort of, or I thought that there would be some sort of repeating pattern in the slope field because I know that the sine of x is periodic. But I have to say that as I look at that slope field, I don't see it yet. So I was a little hesitant. I was wondering when I produced this, did I do something wrong? And we'll come back to that. So Curtis, if anybody has any ideas about those three things that I've mentioned, maybe you'll interrupt and tell me a little bit about that, if there's something in the chat. So part B here is to find a solution to this differential equation that satisfies the initial condition y of 0 equals -1/8. This is a very common type of free response question. Not produce a slope field, but perhaps draw a couple of line segments. Oh, and by the way, Curtis, seriously, I did understand or did hear this morning. I don't think that there are going to be any graphs reproduced in the physical part of the free response portion of the exam that students are going to be writing in.
Say
So,
that one more time, Steve. I'm not sure I understood. And then
so
there's a comment on your
I
window.
don't believe that there are going to be any figures in the actual physical piece of paper that students are writing in this year with the transition to the hybrid exam.
Okay.
So for
That
me,
makes sense.
I believe that means that students will, on the free response, will not be drawing a solution curve. They will not be drawing in little line segments, portions of a solutions curve. solution curve. So any of those types of questions, and it won't be withdrawing, but any of those types of questions will have to be asked on the multiple choice portion of the exam. So I'm not sure I can envision exactly what that might look like. I mean, here I'm just thinking off the top of my head. I mean, you might say, well, here are 6 points and here's a differential equation. Here are four possible um, slope fields for those 6 points, and you might have to pick one of them. So I don't think students are going to have any figures in their piece of paper. They're not going to be drawing on any figures in this hybrid exam. And if anybody can support that and who's watching tonight, I'd like to see if I can confirm that. But
Yeah,
pardon
it'd be nice
me.
to get that ratified for sure. But
Yep.
there was a comment
Yes.
about your window.
Oh, good.
Thinking about a window that includes maybe a full period or even two of the sine curve. So
Excellent suggestion.
perhaps your window could use some adjustment, and then maybe you'd see
Very
it.
good. So it seems like maybe if I went maybe minus 2 pi to plus 2 pi, or at least minus 6 to plus 6, minus
Yeah,
7
something.
to 7,
Yeah.
I might see this periodicity. Right. Very good. We'll get back to that. Excellent, Curtis. So this is still a very common type of question on the free response, and we might see something about this, something like this year. And there's a little added extra twist in this one that I want you to think about. So, all right, the only solution technique that students have or can use, should use to solve this is separation of variables. So the first step is to separate the variables. I've got all the y's on one side, all the x's on the other. There aren't any other constants hanging around, but I often get this question, if there is a constant, where do I put it? And the blunt answer is you put it wherever it makes sense, wherever it's the easiest, wherever it might help you find an antiderivative. And that's the best that I can tell you. So, all right, we're going to take the integral of both sides. We're going to integrate both sides, find an antiderivative. On the left-hand side, it's the log of the absolute value of y minus 1. Yes, you should include that absolute value. And in this particular problem, it's actually quite necessary. So it's the log of the absolute value of y minus 1 is equal to minus the cosine of x plus c. We only need to include one constant of integration. This is the step to include it. Could you put two constants, one on each side? Sure, but you want to combine them into one. Generally, we do this on the right-hand side. And now the next step should always be use the initial condition and solve for C. Some students try to, right after this antiderivative step, try to solve for Y, try to isolate Y, and then use the initial condition. And in general, it is much easier to use the initial condition right now and less chance of an error. So I'm going to plug in the value for x, which was 0, the value for y, which was a minus 1/8. Notice when I do that over here, I get a negative value inside the absolute value, but the absolute value is a 9/8. Minus the cosine of 0. Cosine of 0 is 1. There's a minus 1. I solve for c. It's kind of a little unwieldy, but there's the constant c. I'm going to go back to my solution here, and I'm going to plug in that constant c. There it is. And to get rid of those absolute values, I have to put a negative sign on that argument. Why? Because when I plugged in that initial value, the argument inside the absolute value is negative. That means we are on a branch of a solution curve where the argument is negative. Therefore, to take the absolute value of that argument, which is negative, we have to take the opposite of that argument. Now, we haven't seen one like this on the exam in a while. Maybe Tom can remember, but I don't think we've seen one like this in a while where the absolute value symbols were necessary. So be careful, include them and check. If this argument bluntly is negative when you plug in the initial condition, then when you execute, when you take the absolute value, you must take the opposite of that argument. Okay, now I'm going to try to solve this expression for y. I'm going to exponentiate both sides, take e to both sides. On the left-hand side, I think I'm left with a minus y plus 1. And again, this is kind of an unwieldy constant, but I think it's e times 9/8 because e and log are inverse functions. So there's just a constant 9/8 right there. And I solved for y, and I think I got this expression down here. Beautiful. There's a little bit more simplification, perhaps, with those constants e and the 9/8, but that would certainly be acceptable on the exam. There was no question in my part B about what the domain of this function is. That question hasn't been asked about in a long time, but you might think about that. And I think I've got a part C here. Oh, here we go. So sketch the graph of f on the slope field. Well, I think I said it went through the point 0. Was it 0 minus 1/8, I think. So I'm just going to add a little bit. That's the point 0 minus 1/8. And I sketched the slope field, and I think there's a little bit of symmetry here with respect to the y-axis. And I think it slopes down. It kind of looks like it starts out looking a little bit like a parabola, but it isn't. And Curtis, you're absolutely right. In order to see the period here in this solution curve, I need to extend my window, and that's what I did down towards the bottom because I was a little worried about this. I'm going to extend that window. I think I went from -6 to +6, and I had to go a little bit down in the y direction. I think I went all the way down to -8. And now I can see that there is some repetition here. There is a period associated with this solution curve, as I thought there would be when I was looking at the differential equation in the very beginning. That's kind of cool. All
That
right.
is cool.
I
Hey,
think Tom,
Steve,
yes, sir, go ahead. I'm sorry.
you mentioned a part that hasn't been done in quite a long time. I guess that was part B. Um, I wonder if, since the students are unlikely to be needing to do a question like part C, if something like part B would be a little maybe more probable
Hey,
uh,
good question. Good point.
type
Excellent.
question in there. Just, thinking logic that, if they can't do the sketch, then maybe a little more manipulation like this could be
Yeah.
useful
And-
or something to do. And
Yeah.
then second, I was looking at your part C at your
Yeah.
graphs that at your slope fields, and it seems to me that if you look at the slopes that are returned there around -3 and +3, if you just kind of look up and down,
Yes.
you
Yeah.
do see that there's something happening. That parabola that you kind of sketch, or the parabola looking thing that you
Yes.
sketched
Yes.
in the beginning there. But if you look at some of those other portions of the field, I do see some. Oh, well, maybe there is it flattening out a little bit. So there may be a little bit more of the curve. Of course, your window helps when you go -6 to 6. But I thought there was a little bit that I could see maybe if I looked at the slopes that were returned around 3, it almost looks like we've passed some sort of I don't know. It's starting to flatten out again.
I think it is, and I think that if I really zoomed in around
Yeah,
3 and around -3, or really around pi and minus pi,
right,
I think
right.
you would see flatter line segments there.
Yeah,
That's
yeah.
exactly right.
Okay.
I wonder, Curtis, though, you raise a very good point, since you might not be able to draw on this solution paper this year, if some of these questions would be more extensive. I'm just looking at this, and another question I just thought of would be, I wonder what uh, the absolute minimum value is of this function. I wonder if we could find that.
Hmm.
Interesting. Okay, Tom, you got a little technology?
Sure, Steve.
Okay, great.
Glad to.
There
Okay.
you go. There we go. Yeah, it's working.
Okay. So I'm going to share my screen, and um, Actually going to do a little bit with both the TI-Nspire and the TI-84.
Cool. Okay.
I think what I'll start out with is the Inspire. And let me get my screen shared here. Let's see. There we go. I hope that's come up okay.
Beautiful.
Okay, and what I've got here is just a kind of a blank graphing screen, and I'm pretty sure I'm probably on the function plotter now, but I want to switch over and look at a differential equation plotter, and that's the name on the Inspire for the plotter that'll actually generate things like slope fields for you. So I'll go to menu, down there at number 3, graph entry edit, and we can see all the way to the bottom, number 8 is diffeq, or short for differential equation. And in our entry line, it has a really quite different look to it. And we can see it says y1, and there's a little bit of space there. Do you see that little prime there? It actually says y1 prime.
Got it.
Equals, and then this is where we can put our expression for our differential equation. Now, one tip here is, because you can have kind of a catalog or library of different differential equations you might be switching back and forth to, they have the usual kind of numbering system, just like with functions, f1, f2, and so forth. Here we have y1 prime, y2 prime for the next one, and so forth. What we have to remember is when we put in the expression, if we're going to refer to y, we want to refer to this y, which would be y1. So for the equation that you were looking at, I'm going to type in, it was the quantity y minus 1.
Yes.
I'm going to put in y1 minus 1 to refer specifically to that left-hand side. And that will be times the sign of x. Okay, there we go. Hit enter, and we get a slope field. Okay. So this is a nice slope field. It's something we could plot other functions on top of. This particular slope field, I actually find the default slope fields a little coarse. What I mean is they're pretty sparse. I'd like to have maybe a little bit finer slope field, and maybe more like that second one you did on part C.
Yeah.
And just want to show where we can do that. Let's see, when I come back to the entry line, you see that it's ready for a second differential equation. So I'm going to arrow up to look at the same one we were looking at. And I'm going to go over to where you see that dot, dot, dot. And that says edit parameters. Okay, so let me click on that. There's a lot of stuff here, but the one I'm interested in, I'm going to scroll down. And for a future topic, you can see there's Euler. Okay. But let's scroll down, and I want to go down to where it says field resolution. Okay. Now, as far as I can tell, what field resolution, this is the part that kind of controls how fine the line set.
Oops.
Field.
Uh-oh.
There we go. He's
and
back.
There's a comparable number kind of from, because the window is not a perfect square, there would be fewer vertically. So let me double that to 28.
Okay.
And let's do okay. Now we see a much finer looking slope field there. And you can, put in any number. I just 30 would have been fine too. I just, for convenience, doubled that. I think that number also, you can see, and of course we can change the window too. So but this, I think we're getting a better look at what that slope field looks like. Now, if I wanted to do a sketch of a curve using an approximation method, so this is not plotting that function you were talking about, I could put the initial condition in here where it says x 0, y1, 0.
Mm-hmm. Got it.
Go up there. Let's see, I think your initial condition was when x was 0, y was negative 1/8.
Correct.
Okay, and now
Very
this
good.
is not a symbolic solution. It's actually a solution using that Euler's method that we saw referenced in there. But it gives you a feel for what that looks like. Now, here's a bit of an irony, I think, but it makes sense. I think slope fields, people associate them with differential equations, but I know in my own calculus classes, I pull them out really early. I pull them out when I first start talking about antiderivatives. Because an antiderivative, in a real sense, is a very simple kind of differential equation. You're given a function, and you want something that has that for its derivative. Okay, so that's when I introduce slope fields. And the irony I was referring to is a slope field is very simple-minded. It's just basically taking a whole lattice of points and substituting the coordinates x and y into your differential equation. That's going to tell it a slope. And then it plots a little line segment having that slope centered at that point. And so it does that literally hundreds of times, as you can see in the picture. So it's great work for a machine. However, as neat as a tool as it is to assess students' understanding of slope fields, it's going to be almost always on the non-calculator part of the exam. Because if all you were doing was matching slope fields to a given differential equation, if you had a slope field calculator with you, you just bought them and picked one that was matched. So that they're going to want you to show that you understand what a slope field is. And so they may have you plot one by hand. It's fairly simple. Though I know you were suggesting that might not come up this particular year because of that move to the hybrid exam.
Yeah, yeah. But
the slope field questions are going to tend to be on that non-calculator part. Okay. Now, this is going to be on all the Nspire calculators. It's going to have this kind of differential equation functionality. I did want to show folks, though, that if you happen to have a TI-Nspire CAS, then it actually can do a symbolic solution. Okay. So I've gone to a new page here where I've just got a calculator page. And one thing I was going to try just for fun, see if it would actually work, is go to the menu, go to calculus, pull up an integral. And what I'm going to do is, this was an early part of your symbolic solution, Steve.
Okay.
So I think you had, let's see, 1 over, whoops, I got in the...
We got a couple of fans of the Nspire cast.
Oh, good.
All right. So in the integration, I'm not going to put any limits of integration here. I'm just doing symbolic integrals here. So
okay.
1 over the quantity y minus 1.
Minus 1, yeah, right. Right.
And we're integrating that with respect to y. So this is that step after you separated the variables.
Correct.
So that's one side. And then we'll have an equals. Whoops. Let me get outside of the integral there. Okay, gotcha. There. Now I'll pull up another integral. So I'll go back to my calculus menu, pick up integral. And again, these are totally symbolic. I think this side was just sine of x dx.
Correct. Yep.
Okay. And I'm just curious what it's going to do with this. What if I just enter this line from that first step you did? So I'm just going to hit enter and we'll see what happens.
How about that?
Shift plus.
What's that?
Shift plus for integral.
Oh, okay.
Is that
To
true?
save a step for hunting it down under the menu.
Yep.
Okay.
Yeah, just hold down the shift key and the plus. Is that true? What?
That's pretty cool, Tom.
Yeah. Though we should notice something here. Something's missing.
Yeah.
We need a arbitrary constant on at least one of those two sides of that thing, right? To kind of take the next steps here in solving that. So that's giving us an antiderivative for each side. Okay, so that's one issue there. And so you couldn't do this on a non-CAS machine, but that's there. But there's also a differential equation solver on the Nspire.
Mm-hmm.
What that looks like is we can just type in DE for differential equation, solve. And the way this works is you put in your differential equation. So I'm just going to put in y prime equals y minus 1 times sine of x. And then we put the independent variable, which is x, and then the dependent variable, which is y. Let's see what happens. Boom, there it is. So there's the symbolic solution there. And if you're looking at that C6, that's just a placeholder for an arbitrary constant. Okay. So it looks pretty neat.
Sure does.
And this one is taking care of that arbitrary constant. So that's nice. Moreover, you can also do these with that initial condition. So I'm just going to copy that down again and make a little bit of an edit. So after my differential equation, the y prime equals y minus 1 times sine x, I'm going to type in and y of 0 equals negative 1/8.
Oh, that's cool.
There it is. So there's our solution with that initial condition. So because CAS machines, they are allowed on the AP exam, it becomes pretty clear you're not going to see a differential equation problem on the calculator open part of the exam because it's just not going to be a level playing field. For a CAS, it's just going to be able to do some of these, right? So they're going to test your understanding of differential equations on that calculator closed part of the exam. Nevertheless, I think this is a nice tool for checking answers and for visualizing solutions. I love the slope fields. What I'm going to do is I'm going to switch over to
Before you do that, Tom, before you do
Yeah.
that, one quick question. Would you copy that expression for y and then graph that function on that slope field that we had a minute ago?
Oh, okay.
Yeah, hit arrow up. Oh, there you go. Yeah, that's fine.
Yeah. Okay, so let me do a copy. And then let's see, we'll want to go to
You want to go back to window?
Back up page to the
back a page, I believe. The 1, 2, yep.
Yeah. Let me go to menu, do graph entry edit.
Yeah.
Get a function plot.
Yeah.
And let me hopefully paste will work.
Hopefully, here. Yes.
Let's see, did it?
Control V.
That's what I thought I did here. Let's see. Control.
Or are you on a
Mac? There we go. All right. I just didn't hit it hard enough or something. Okay, there it is. I think it's good.
Great,
Let me hit enter and see what we got.
Oh, that's exactly what I thought would happen. Okay, so do this for me, Tom, and then I have a question for participants, okay?
Okay, sure.
So would you just kindly change the window, and I really only want to change the Y min and Y max. We can leave the X's. Well, we could go a little bit farther on the X's too, I suppose. So let's go window settings. Great. Let's make that minus 12 to plus 12.
Okay.
And then on the Y min, let's make that minus 8.
Okay.
And y max, let's try +3.
All right.
Beautiful.
Give it a shot. See what we get.
Excellent. Oh, phenomenal. That's terrific.
And
So,
what's really nice that I wasn't sure about when I first tried it is, I switched over to the function plotter.
yes.
But it did go back and redo the slope field too.
Yes, it did.
Right.
It did.
Yes,
And
it did.
that's really nice. That's something you would want to have happen here. And it does. So
So
also you can really see how the numerical technique,
right.
as you get away from that initial condition point, the error does increase a bit. Yeah.
Exactly. Yep. This is a great example of that. Yep.
Yeah. Very neat. Okay, great suggestion.
Cool.
Curtis, did you have something from anyone that?
No, I think we're good.
All right. So
I had to look back to the chat there.
okay. So I'm going to do a stop of the share of the Nspire, but I'm going to go ahead and share quickly what you can do with slope fields on an 84.
Okay.
Okay.
Sounds good.
Let's see. I'm trying to find my 84 on here.
So one thing while Tom's doing that, Curtis, is participants can think about if you picture that graph that Tom had a little while ago, and it did show that the numerical solution was off a little bit to the exact solution curve. So one might think about why that's happening and where that's happening and where is it very close to the solution curve. And I wonder why that's true. So there's some good questions in there to think about, good conceptual ideas to think about in there.
Okay. Is that coming up okay?
Yep, got it. Got it, Tom.
Okay. All right. Okay. First off, this is one of the I'm not one who on the 84 really loads up my 84 with lots and lots and lots of programs, but this is one program I feel like it's a must-have for the 84. It doesn't have a built-in slope field plotter, and so I think lots of people have written slope fields. I'm going to put in one that I think it was originally one that a guy named Mark Howell, a colleague, had written up, and I've tweaked it a little bit. But the way this slope field program works is it's going to expect that you put your differential equation expression for the derivative, your dy dx, into y1. So this is going to look a little bit strange, but I'm actually going to put in the differential equation expression that we had for this problem, which was, let's see, alpha y, there we go, y minus 1, that quantity times sine x. Now this looks really strange because we're never used to seeing y show up in a y1 expression. But this is just it's a placeholder for our differential equation expression. So once that's stored in there for y1, I can quit to the calculator screen. And let me just clear that out. I'll go to programs, and in my TI basic programs, I have a program here that says SLP FLD for slope field 2. That's because I did some tweaks to it. All right, so let me enter that, and I'm just going to enter again to run it. And what it should do is plot a slope field for that differential equation. Now here it looks like the window is a little bit weird. So let me do a zoom. Let me do a zoom decimal to see what that looks like. Now that changed the window. So I'm going to need to run the program one more time.
That's looking a little better.
Yeah, it's looking much more kind of like that first one you had. Though it actually has a Y range that gives us a little bit of a look at the periodicity because it's running almost from -2 pi to 2 pi. And so this is one where, again, we could plot a function on top of that. I would need to use y2 or something like that. So for example, if I went to the y equals and went to y2 and plotted our 1 minus, let's see, was it E? Let's see. Oh, I missed my coefficient here. So let me put a 9/8.
Yep, there you go.
Times, and I'll do an E. And I'm actually going to put a 1 minus cosine x up here, which will be equivalent to the one you had. I think you brought the e to the first down too.
Yep, exactly.
There we go. So I think I got through that without making a mistake. So let me enter that. And now if I go graph that, it will graph it on top of the slope field.
That's really nice, Steve.
It is. It's
very cool.
Steve, we got an answer to your question, and actually I was thinking something similar, not quite as articulate as Wanda, but the Euler's method using tangent lines is really kind of the explanation for what you've got going on there. So the slopes change more rapidly. The tangent lines need to be smaller step sizes to kind of keep up with those approximations, right?
Very good.
So
that's a fantastic.
You do better when the slope is steeper. You do better when the slope is steeper because even you don't have to sample as finely along the x values as you would in order to get accurate representation when the slope is not as steep.
Oh yeah, fantastic explanation.
Pretty good.
Yeah,
pretty good.
Okay. All right,
great work.
So just one last thing. So like I said, this is a fairly simple program. And for me, it's really a must-have because on the 84 if you're going to use it in calculus, because you either this program or one like that. And Curtis, I can make that program available where you can post it. It's on the TI website, but if people want to get hold of it.
I think it'd be easier if we just posted in this YouTube description.
Okay, sounds good. One last thing, this program, it doesn't just automatically erase this slope field unless you go change your window. If you change your window, it'll erase the slope field. But if you don't want to change your window, if you want to just clear your screen, just go to the draw menu. So I'm going to, it's this shift of program. And that very first thing, clear draw, clears the slope field. And now we just see the solution there.
Gotcha.
So, okay. All right, Steve, I think I'll stop sharing.
Very cool.
Very back cool. Over to you.
Okay. Thanks, Tom. Neat stuff. Okay. All right. Here's problem 2. Now, again, as we were saying, we might not see something like this on the free response portion of the exam, but somehow, I don't think these problems have gone away. Somehow they will test students on this. So this one says we have a differential equation. This time dy dx is y times x minus 1. And a typical sort of problem has been on the axes provided, sketch the slope field for the given DE at 6, 8, 9 points indicated. I have 9 here. So what we have to do is recognize the coordinates of each one of these points, plug them into this differential equation, recognize that that is the slope of the tangent line, and draw a small line segment with that approximate slope. Now, often in these problems, many of the slopes turn out to be 0, and that's the case here. So here's a notation that I might use that says, find dy dx and evaluate that where xy is equal to 1y. So for any coordinate, for any point where x is equal to 1, and I plug in a y, well, I'm going to have a 1 minus 1 here. That's a 0, and so the slope is going to be 0. And so that immediately told me that these line segments here along the line x equal 1 are going to have slope 0. Now, I won't do all of these, but let me just do one or two more. So I switched over here to take a look at what happens when x is equal to 2. And let's look at this first point right there. So that has coordinates, I think, 2, 1. So let's see, here's my y value. There's my x value. So that's just a 1. So I do my very best on the axes provided to draw a line segment that has slope 1. And I frequently get this question about, well, when this sort of a problem was scored, how accurate did those slopes have to be? And really what we're looking for is sort of the relationship between the slopes. For example, if I take a look at the next one, just one more here, Curtis, if you don't mind. If I take a look at the derivative, dy dx, where xy is equal to, well, let's say 2, 2, well, here the y value is 2, x is still 2, and now I've got a slope of 2. And so when I draw that line segment, it ought to have a little steeper slope than the one just below it, the line segment just below it. And you know what's coming. This line segment ought to have a slope of 3, a little bit steeper than the two below it. Okay, so I've drawn those 9 line segments. Let's take a look and see what part B says, a little different here. This says find the second derivative of y with respect to x in terms of x and y. And this seems sort of funny. It says determine the concavity of all solution curves for the given DE in quadrant 1. Let's see if we can give a reason for our answer. Well, all right. Here's the differential equation. I rewrote it up above. And what I need to do is take the derivative of both sides with respect to x. So in a sense, I have to do this implicitly. So the derivative on the left-hand side is, well, d squared y over dx squared. And on the right-hand side, I have to use the product rule. So it is the first expression y times the derivative of the second. The derivative of that expression is 1, plus the derivative of the first expression. And I will write that for now just as y prime. I could use dy dx, but in these sorts of problems, I think using y prime is a little bit easier. You know, notational fluency. And I think it's just easier to work with that one symbol y prime rather than writing out dy dx again. Well, I have an expression for y prime. There it is. So I substitute it in, and I did a little bit of simplification. And here's what I have for that second derivative of y with respect to x. Now, Curtis, you're absolutely right. That expression within the parentheses, I could multiply out that binomial and I could collect some terms and rewrite that a little bit differently. But I left it like that for a reason because I thought a little bit about what's coming. In quadrant 1, I know that y is always greater than 0, and for any x value, this expression is always positive, and I'm adding 1. So I know that expression inside the parentheses is always 1 or greater. So I know that the second derivative is always positive. And that means the second derivative of y is always positive. And that means that the solution curves must be concave up in quadrant 1. That's a nice problem. We have seen problems like this on the exam similar to this, where students have been asked to find a second derivative and to do some analysis with that. Here's another similar one down here in part C. It says, let's let y equal f of x be a particular solution to this dE with the initial condition of f of 2 is equal to 2. I want to write an equation for the tangent line to that graph of that function at x equal 2 and use it to approximate f of 2.1. Well, all right, I'm going to add in a little bit more up here. I'm just going to translate some of the words into mathematics. I know that a point on the curve is 2, 2. There it is. In order to get an equation of the tangent line, I need the slope. So I do that by going back to the differential equation because I have an expression for dy dx. And in fact, if I've done everything correctly, I already figured this out back in part A. dy dx at 2, 2. 2 times 2 minus 1, well, that's just 2. So here's an equation of the tangent line, and I rewrote this in slope-intercept form. Okay, So I'm going to use the equation of the tangent line to approximate the value of the function at 2.1. That simply means, okay, that's my linear approximation. I'm going to let x be equal to 2.1. I'm going to plug that in. When I do that, I got a 2.2. That's my approximation to the value of the function. Now, you know what's coming here in part D. Is that estimate an overestimate or an underestimate? And justify your answer. Well, why is it an underestimate? Well, it's because I know that all of the solution curves, I'm in quadrant 1, all of the solution curves are concave up. Therefore, my tangent line at any point on that curve must be below the curve. It's concave up. And therefore, my estimate here is an underestimate because that solution curve is concave up. Now, I'm not satisfied. Perhaps I want to see this graphically, so I added another part to this while we're here. Let's find the particular solution to this differential equation with that initial condition, 2, 2. So let's go through this again. We separate variables. We find an antiderivative of both sides, and there's the plus c. Don't forget the absolute value. It's the log of the absolute value of y is equal to x squared minus 2 minus x plus c. We find an antiderivative, or we integrate term by term on the right. I'm going to use the initial condition. There's y equal 2. There's x equal 2 plugged in there and there. And I think that simplifies to c is just a log of 2. How about that? So I know that this argument for this particular solution is positive. So that means, how do you take the absolute value of a positive argument? It is just that argument. So bluntly, I can drop the absolute value symbols here. So here's my expression. I'm going to solve that for y. I'm going to exponentiate both sides, e to both sides, do a little bit of simplification, and I think there's my expression for y. 2e to the x squared over 2 minus x. It's kind of hard to see. I'm sorry about that, Curtis. It's kind of a small font, but that whole expression, x squared over 2 minus x, is that subscript or is that exponent on e? Is that superscript, excuse me.
Yeah. Mm-hmm.
And I just wanted to double check this and put all of this together. So down at the bottom, I didn't ask for this initially, but there's a slope field, a bigger slope field for this differential equation. If you can see the color, the blue curve is the solution curve that goes through the point 2, 2. And the maroon line is the tangent line to the curve at the point 2, 2. You can see the concavity. It's concave up in quadrant 1. And you can see this, you can visualize that my estimate using the tangent line at 2.1 is going to be below that solution curve. That's kind of cool. Tom, should I continue with number 3?
Maybe I could show something real quick, Steve.
Okay, deal.
All right. Okay.
Very good.
So let's
there
see.
we go. How about that? Sorry, Tom.
Oh, no problem. Okay. I'm going to share my 84 screen. And I went ahead and took the liberty of putting in, for a slope field, I put into y1 your expression for the derivative, which is y times x minus 1.
Okay.
So I wanted to take a look at the slope field for this, but I wanted to do it like really close to that point that you were interested in, which was
2, 2?
2, 2.
Okay.
So I'm going to go to, before I do my slope field, let me go to the window. And I want to center my window at 2, 2, but make my window very small.
Okay.
So what I'm going to do is I'm going to make my x min, say 2 plus, well, let's say just, I'll tell you what, let's just make it 2.2.
So you want to go to the, you're going to go to the right of 2 here, Tom?
And then I'm going to make, oops, excuse me. Good point. Let's go from 1.8
Okay.
2.2. Yes, I want to go
Okay.
2 minus 0.2 to 2 plus 2.2. Yeah.
Okay,
Thank
gotcha.
you for
I gotcha.
catching me. That would have been and Y min, Y max. Let me do a similar thing. Let's go from 1.8, except I don't want it to be negative, to 2.2.
Okay, gotcha.
Okay. So there's my window. And now let me do a slope field.
Okay.
I'll bring up the program, slope field. Now that may look kind of strange, but it actually makes a lot of sense. Is almost all of those line segments look like they're about the same slope.
They do, yes.
And that's because I'm really close to, the whole window is pretty close to 2, 2. And at that point, I think your slope is actually 2.
Correct.
So this is not surprising, as the slope field is reflecting that. It's also suggesting that if we don't move too far from 2, using that slope of 2 for a tangent line approximation, for example, won't be a bad approximation. It will be off a little bit, but as long as we stay fairly close to 2, it should be pretty good. So that's the only point I wanted to make is if you use slope field on tiny windows, it may look pretty uniform. All right, I'll stop.
And that it makes sense that it looks pretty uniform is kind of a cool. That's kind of cool. I mean, this idea of local linearity and
exactly. Yeah, that's what we're seeing. Yeah.
It just, you're seeing it in a far broader sense right there. That's kind of cool.
All right, Curtis, we've got one more. I think maybe we can get through this one. And there's some interesting questions, I think, in this last problem, number 3 tonight. Again, we have a differential equation, e to the minus y, x squared minus x. Y equal f of x is going to represent a particular solution to this dE, and it passes through the point, that's kind of weird, 2 log 6. So the first thing I asked about was to sketch a slope field for this differential equation. So I expanded my window a little bit on this one. I went -4 to +4 in both directions. And I'm not going to go through too much of this, but there are several things that I'd like, again, participants to think about here. Here's a couple of them. I think I've got about 4 things to think about, Curtis. So here's one of them. If you look along the y-axis, it looks like all of the line segments have slope 0. If you look along the line x equal 1, it looks like all of the line segments are 0. Kind of figured along 2 and 3 and all the integers they'd be 0, but they aren't. So what's going on there? And this also seemed kind of weird to me as I look up here with y values, oh, I don't know, bigger than 3, bigger than 4. It seems to me like the line segments are all having slope 0. And I wonder why that's true. And as I get down here, at least over on this side and at least to the right of 1, it looks like all of those line segments have slope, well, very large, either very, very large negative or very, very large positive. And I wonder why that is. So there's some things to think about. I think that's the right slope field. I wonder if you can answer all of those. Okay. Let's solve this differential equation kind of quickly and then see what this leads us to. So we want to find the solution to this dE that satisfies this initial condition. What was it? Oh yeah, f of 2 is equal to the log of 6. Okay. So I separate the variables. I've got all the y's on the left, all the x's on the right-hand side. We integrate both sides. On the left-hand side, I've got e to the y, probably the easiest antiderivative we can find. On the right-hand side, we integrate term by term. X cubed divided by 3 minus x squared over 2. There's my plus c. Third time we're doing this tonight. Generally, we couple the constant with the x's. Doesn't have to be, but generally that's the way we do it. At this point, I'm going to use the initial condition. So I let's see, x was equal to 2 and y was equal to the log of 6, okay? So I did a little bit of simplification. Again, e and log are inverse functions, so I get a 6 on the left-hand side. I did a little simplification on the right, and I solved for c eventually, and I got a 16/3. Holy Toledo. I'm going to go back up to this expression. I'm going to let c be equal to 16/3. And this really isn't that bad. I'm going to solve for y. This time, what I have to do is take the log of both sides. So y would be equal to the log of this argument of this expression. Beautiful. Now, this might be a neat problem to think a little bit about what the domain is. And here's why I thought about that. Well, I know that if I just had y is equal to the log of x, we know a little bit about that function, and we know the domain of that function, and it's not all reals. So I'm wondering, does that argument of the log in this expression, in this function, does that ever become close to 0? Does it ever equal a negative number? Well, here's what I did. The very first thing I tried to do is to sketch the graph of that function f on the slope field. We've been doing a little bit of that tonight, and so there it is. I think this point right there is that 0.2 log 6, and there's a sketch of that solution curve. Now, when I drew that, when I sketched this with Mathematica, I was a little concerned about this. It does seem to follow the slope field, so I felt good about that. But I was a little worried about, well, what's going on over there near -2? I don't quite see what's happening. It just seems like the solution curve ends. So I'm going to arrow up a little bit and try to explain how I did a little bit of exploration with my TI-Nspire. On the left-hand side, what I did was simply define this function f, and I wanted to learn a little bit more about the argument of that log function. In other words, is it ever positive? Pardon me, is it ever negative? I know it's a cubic. I know what the general shape is. Seems like, gee, it's probably negative somewhere. So I drew the graph on the right-hand side, and I used a built-in function of the TI-Nspire to find that 0. And it does indeed cross the x-axis at -2.1 roughly. So what does that mean? Well, I'm going to do a little bit more scribbling here, if you'll allow me, Curtis. I'm going to rewrite, if I can find it here, I'm going to rewrite the solution curve. It was y is equal to the log of x cubed over 3 minus x squared over 2 plus 16 over 3. What is going on here? What is that graph in the bottom right-hand side telling me? Well, it certainly means that the domain of this function has to be x greater than -2.106 because that argument cannot be negative. But it also means that this argument is getting closer and closer to 0 through small positive values. So what does that mean about the solution curve? If that argument is getting closer and closer to 0 through small positive values, jeepers, what should the log be doing? And therefore, what should that solution curve be doing? Any chance of one final answer on that one, Curtis?
So your question is what's happening for small positive values for the solution curve?
Yeah, well, for small positive values of this argument, so that argument is getting closer and closer to 0 from the right as x gets closer to -2.1. So what does that log of that argument do?
Going to approach 1? Negative infinity, I
Yeah,
guess.
that's better. I think it ought to be going off to -infinity. And so this solution curve ought to be going down something like that. So the question is, why did it stop right around there? And it has to do with the way that it's sampled.
It must be. It must.
Oh, it does. It absolutely does. Has to do with the way, the points that were sampled in drawing that curve.
Did
But
you
that
try drawing that curve on the Nspire?
I did not.
I tried it on the 84 if you want to see.
Okay.
All right.
Seems
Cool.
like this ought to be a really nice. This seems like a pretty interesting curve on the Nspire to try drawing as well. And Wanda, thanks for the negative infinity coin too.
So here's that function that was the solution.
Yes.
And here I'll just take a look at a zoom decimal window, usually my favorite. And we're getting much better. Yeah, it's looking much more asymptotic as you get just a little bit to the
takes
left
off a little bit better. Mm-hmm.
So that must have, Tom, correct me if I'm wrong, but that must have sampled at -2 and -2.1, correct?
I think
Correct.
so. Let me do a trace. Yep. And we can. Oh,
100%.
Like I got the polar on there. All right.
You said zoom decimal, so I know that the trace steps are 1/10.
I need to. Yeah, I think I've got rectangle.
It will for sure.
We were doing.
We were doing Polish before, yeah.
Right there. So here's our graph tracing.
Okay.
There we go.
Yeah. Okay. Go ahead.
And if I could go to -2.
Okay.
And if I trace one more to the left,
yeah,
2.1, and it's going to jump over it after that. So now I could try putting in -2.106.
How about that?
And it's true. And it's just a little bit less than that is where we're going to hit that. So that's actually off the screen as we
Yep. So that's very, very steep there, right, Tom? So that's
why, we can see it visually how steep it is.
That's why the sampling did not reach that.
Yeah.
Just because I know you have the software open and we're already over on time. Can you go to your Nspire and graph that?
Sure. Let's see. Let me switch over to Nspire.
I would just love to see if the way that Nspire graphs that, the sampling and all that, if
it's any different, yeah.
If it's any different, I'm suspicious it
but
I'm just curious.
Okay, and I think let's see.
You just need a new just Control I and put in a new
graph screen.
Let's put in a new.
Yeah, there we go.
Just a new graph screen. Get you a clean sheet of paper.
We're looking at it was natural log of x third divided by 3.
Yep.
Minus x squared.
Minus x squared over 2, right?
Yep.
Divided by 2 plus 16/3.
Yep.
16 over 3.
Oh, that's pretty good.
Yeah.
I thought that Nspire you would have a more pure picture, if you will.
That's an excellent point, Curtis, and actually goes to the point Wanda was making, is where this graph is steep, the TI-Nspire plotter actually knows to start sampling finer and finer so that it has a more accurate graph.
Yeah.
While the kind of the graphing pixels on the 84 or at fixed increments, the Nspire kind of does adaptive graphing in an effort to make it as accurate as possible.
Pretty cool.
Love it.
Yeah. Good deal. Okay. And I'll stop the share there.
All right. Well, we're over time a little bit, so we'll sign off here. I put my email in the chat, curtis@ti.com, so please email me for the PD certificate. And then also, I will be posting the solutions tomorrow. Steve will get those to me. Go, as well as a program for drawing slope fields on the 84. So thanks very much. We'll see you guys in 2 weeks.
Very good.
3 weeks.
Correction. We'll see you guys in 3 weeks.
Okay.
All right. That'll do it.
Very good.
That will do it.